Thanks, Steve, and it's my pleasure to be with you this afternoon. We're going to discuss fundamentals and behavior. It's not about design in the sense that you have to do on a daily basis. It's about understanding the bases for that design, and I hope there will be several points during the presentation when you say, gee, I didn't know that, or that feature was never explained to me properly. As we go through those fundamentals at the appropriate locations, I will talk about the specification requirements, but it's not the specification requirements first and the explanation afterwards. So we'll try to develop our understanding of how individual fasteners behave, then how those fasteners behave in joints. Sometimes that's a little different, and then the specification rules that reflect those issues. Now, we have to have a point of view, and the point of view is that you're a structural engineer. I appreciate that not everybody is a structural engineer, and indeed the mix is helped for all of us if there are some inspectors and people from fabricators, and sometimes there are erectors, and I think we have those others here too. So you won't be shortchanged. There is stuff there uniquely for you. But as a structural engineer, it's a lot different than for welding. All the responsibility devolves on you. You have to pick the right bolt types and grades. There isn't anybody else. You have to design the fasteners. You're responsible for the installation, and you're responsible for the inspection. Now, probably you don't do all 4 of these tasks, but at some point you're going to be asked from your inspector, for example, gee, I have some problems. They didn't do this or that, and I'm going to try to give you a stronger background in those areas of installation and inspection so that you will be the resource person. Mechanical fasteners, they're pictured here. They're marked on the heads. It's a matter of picking it up and reading it. And likewise, nuts are marked in a unique way. Let's start with rivets, though. Why would we need to talk about rivets? And we're just going to say more or less the next few minutes, and that's all. It's particularly the evaluation of existing structures. When you think about it, there are tens of thousands of railway bridges out there, for example, and railways can't simply abandon them and say we'll replace them all because they're 110 years old. So you as the engineer have to be able to evaluate existing structures that are riveted, and usually that means evaluation for fatigue, not always. In the resource that Steve mentioned, which is AISC Design Guide 17, there is additional information there on specifics relating to rivets. But we're going to talk about bolts, obviously, and there are these categories being common or ordinary bolts. The ASTM designation is A307, or the high-strength bolts, which I'll be describing, A325 and A490. There are other high-strength bolts, but they don't occur often enough, frequently enough in structural practice, and we won't spend time on them. So let's start with A307 bolts. There are 3 grades, cleverly called A, B, and C. We're only interested in A because the others tend to be general piping systems or anchor bolts or studs, and we now use other fastener material for anchor rods, as they're now called. So looking at grade A, the minimum tensile strength is 60 KSI. Tensile strength is the benchmark that we're going to hang our hat on throughout this section on strength. We have to have a starting point, and the starting point is let's do the tensile test. Either you do it or presumably you pay someone to do it. It's an easy test to do, and it's the benchmark. Now, if the fastener is acting in some other way, which is the more common situation, most bolts, for example, operate in shear, we have to have the linkage between our acceptance test, in this case 60 KSI, and the shear strength, and I'll be developing that. These are a decent choice when the loads are static. They're cheaper than the other fasteners. The strength level is inferior to what we'll be seeing in a minute. The 60 KSI, though, is consistent with a lot of grades, strength of a lot of grades of structural steel. If we need pretension, and we're going to have to talk quite a lot about that, the pretension here, there might be some, but it's indeterminate. We just don't know what it would be, and so we don't count on A307 bolts for pretension. Turning to the high-strength bolts, there are two types, 1 and 3. As you might expect, there was a type 2, but that no longer exists. Type 3 is weathering steel. We don't have to know what type. As a designer, you just pick A325 bolts and you're finished. Type 3 is weathering steel, but the properties of weathering steel, insofar as the strength is concerned, are the same as type 1. So that's easy. Then you go to the ASTM spec and see what they have to say. And among other things, they give you the chemistry and some of the physical dimensions and so on. And they say, in effect, here's our product, but you must use it in accordance with another specification. And I don't know if that ever occurs in any other ASTM spec. And that other specification is that's put out by the Research Council on Structural Connections. Now, you probably haven't seen that specification. You should. It's got a lot of useful information in it, particularly commentary. It's the fundamental source for the strength issues concerning high-strength bolts. We'll come back to that. Now the minimum tensile strength is 120 KSI. In other words, it's doubled over what we had a moment ago with the common bolts. Or if the bolts are greater than 1 inch in diameter, it's 105. That's an artifact. We never did use that as designers or specification writers. We always use 120, not the 105. And it shouldn't really be there. It should be out of the specification, and I'm encouraging those people who are involved in that to try to get that removed so it's consistent with how we do things. Now, if we need pretension, we can get it. It can be induced. And as I said a few moments ago, we'll talk about when we need it, how we get it, and how we inspect for it. The pattern with A490 bolts is very similar, type 1, type 3. Same answer, you don't have to worry about that. Unless you've got a bridge with weathering steel main stuff, then you use weathering steel bolts. That's where you'd use it. Minimum tensile strength has gone up again, not hugely, 150. We're at the point now, though, where the steel is always ductile, and we want to keep it ductile. We want to detail so that our connections are ductile. There's an upper limit placed here now of 170 because at about this level, things start to get brittle and we get failures that we don't want. So there's an upper limit. There wasn't for A325 bolts, or there isn't. The same relationship between the ASTM spec, which you as a designer probably don't use on a daily basis, maybe on a lifetime basis. They say, here's our product, but you have to use it in accordance with this other spec. And, of course, if we want pretension, then we can induce it. So here's the big picture. Happens to be for 7/8 inch diameter bolts. These are the tension tests. Just put it in a testing machine and pull it. The A307 bolt has a characteristic stress strain curve that's similar to that for mild steel, isn't it? These curves, and almost all the curves I show you, are real. They're not just representations of. I just don't put the data points on them. It clutters things up. We're not altogether sure what's happening in here. You might say there's a yield point. You might not see one. But clearly for the other two types, in these regions of the need, there is no yield point. It's a high enough strength steel that doesn't show up. And that's typical of high strength steels. And why is this important? It's important because we have to appreciate that there's no basis for design that relates to yield of the bolts. I'll come back to that too. So what else do we see? Well, we see these happen to be tension versus elongation. It could be stress versus strain. We see a long curve here like we would see for mild steel, and a little less ductility for the A325 bolts, and again less for the A490 bolts, but still ductile. Just to repeat, we're dealing as the starting point with the ultimate tensile strength of the bolt. So we need a relationship between that and shear, particularly. That's the major case. We'll come back to that. But let me reemphasize, what about yield strength and what about something called proof load? Yield strength, I've already introduced the idea that there isn't one for these steels, and there isn't. I'll try to reinforce that as my talk goes on. But you'll also see in the ASTM spec reference to a proof load. Proof load as a generality is the load up to which, the level of load up to which you can load and then unload without more than a certain amount of permanent set. I don't know why it's there. It's just probably put in there to aggravate us. It plays no role in the design of the fasteners, their installation or inspection. So you can take that and set it aside. Nuts, obviously we're going to need nuts. The ASTM spec for that is 563. And as far as we are concerned, once you've picked the nut that's consistent with that fastener, let's say you're using A325 fasteners, that specification will tell you which nut to use, or which nuts. I think you've got a couple of choices. So once you've done that, you have a nut that will not fail before the body of the fastener fails. So that's all the design that's involved in that case. We don't do the design. That's been done. It's historically available, and we get on with it. If we need washers, we don't always, and there's a specification for them. Sort of an implication to this point that we're talking about bolt, nut, and washer sets, and often we are, but that's not always the situation, and other configurations are available. With that introduction about what we're using, the fastener itself, let me talk for a few minutes about the loading of the bolts. I hope for most of us this is going to be simple review material. It's going to make you wish, though, as you probably wish almost on a daily basis, certainly weekly, I sure wish I'd learned that material in second year that we call mechanics of materials or strength of materials. That's so fundamental to what we do as structural engineers. So when we talk about loading of bolts in shear, the load transfer is by shearing the bolt or bearing in the connected material. We call those both shear. More explanation to come. Or the load transfer can be by friction if we've pre-tensioned the bolts, and more explanation to come. Or we can have tension loads that we have to carry, and we'll look at that, and we can have, of course, combined tension and shear. Most connections, the bolts are in shear, many connections they're in tension, and occasionally they're in tension and shear. So we have to be able to handle all of these possibilities. So here's a simple connection as I can show. Almost all my illustrations are going to be with plates, but that doesn't restrict things. You know, whether it's an eye or a channel or a W shape, the principles apply. So we look at this and we say, well, we've got 12 bolts. How is that load transfer happening as I go from the left to the right? And how do I drag that out? Well, in this case, your presumption is that it's being transferred either through 6 bolts or 12 bolts. But we can't guess at these things. How do we extract the answer that represents the situation as it exists? You draw free body diagrams, back to maybe even to first year now. First year or second year says draw a free body diagram. Which free body diagram? The right free body diagram is the one that gives you the answer that you're looking for. There's no other way of saying it. And in some cases, you'll see it immediately. In other cases, you're going to have to draw free body diagrams until you've got the information that you require. Well, we better speed this up a little bit. So let's draw a free body diagram through that splice location where there's a gap in the main plates. And that enables us, I'm not going to draw this one, enables us to see that starting from the left, all of the load passes out through the first 6 bolts into the lap plates. Now it's all in the lap plates, and as I proceed to the right, it passes out of the lap plates back into the main plate on that side by way of the other 6 bolts. So it's never carried by 12 bolts. it's carried only by 6 bolts. So you sort that out. Here's a somewhat more busy connection, and we could start perhaps mentally from the inclined member and think of that inclined force as a vertical and horizontal component. The vertical component has to be balanced by something, and the something in this case is the vertical member. We still have a horizontal component for which we have to obtain equilibrium, and that shows up as the difference between the right-hand chord force and the left-hand chord force, which are different values. So the free body diagrams will lead you in these directions. Sometimes we have to do a little more. In the case of eccentric loading, we have to do a little more calculation that takes account of the additional effect of the eccentricity of the force. But you have to do that. We have to do that. You need help sometimes. It's available. We're not doing it here. So-called standard beam connections, where you have one line of bolts, it would be reasonable. Experience shows us that it's reasonable to neglect the eccentricity. If you have 2 lines, then you usually include it because it does have a more significant effect. So those bolts are in shear. Let's leave that for a few moments and look at bolts loaded in tension. This is a pretty obvious example. Occurs occasionally. A hanger, bottom flange of a W shape, and there's a channel and there's a T. The channel is here. The load passes out of the channel, in this case by 4 bolts, by shear, free body diagrams. Now it's in the stem of the T. From the T it has to head on up into the lower flange of the W shape. And that's the orangey bolts that we see here. I'll draw one free body diagram just so we can reinforce some of the things I've said. So those bolts are in shear. You either know that or you draw the free body diagrams. And those bolts are in tension. Let's draw the free body diagram that corresponds to that. As I said a few moments ago, which free body diagram? The one that gets us the answer that we want. We want the forces in the bolts that connect the T to the lower flange of the beam. So we pass a cutting plane through there, through that intersection, and now we'll see it come into play. Put on the known forces, put on the unknown forces as unknowns. Write the equations of equilibrium. Sum of forces in the vertical direction, of course, will give me the force in the orangey bolts, which are the bolts that are acting in tension. The presumption at this point is that the total load is divided by 4 in tension. It's a little more complicated than that, so we haven't quite finished with this. Before we get back to that, here's a busier connection. It's an all-bolted moment connection where both shear and moment are transferred. When rivets were used, this kind of connection was used a lot. It certainly has fallen out of fashion in recent years, but to some extent it's coming back in seismic design. But this is all bolted, just so I can show you things. And we would start by resolving the moment into a force couple. If you'll watch, it will appear before your very eyes. That set of forces acting at the level of the flanges is a good approximation of the moment. In an I shape, most of the moment is carried by the flanges. Remember that? Most of the shear is carried by the web. I mean, that's supportable. It's not just somebody's idea. So when we do that, then we can proceed, let's say, up to the top to find out what the forces are in the bolts that are sitting up there, including the ones that are in tension, which are the ones that I wanted to deal with, those bolts in tension. There's the free body diagram. A little bit of work will elicit the information that the shear in those bolts, there's a little eccentricity there, isn't there? But that's negligible, and it can safely be ignored. And then that gives me the force, the tension force in those 4 bolts, 2 here and 2 on the backside. Before we leave the bolts in tension, I have to say another word, and that is the way that connection deforms has an effect on the forces. For the ones that I've been showing, I said that the force in the bolts would be the total load divided by 4, because they're 2 bolts on the side we're seeing and 2 bolts on the back. But this, depending on the flexibility of the various parts, this acts like a lever. Well, that doesn't depend on the flexibility. It acts like a lever, and the bolt force will be greater than P/4 as a consequence. So we have to have a way of calculating that. We're not going to spend our time on that, but I'm pointing it out to you. You have to make that calculation. And it can be considerably higher. It can easily be 20% greater than the P/4 calculation. It can be high as 30%. It can be more than that, but I'm talking about conventional or common practice. Indeed, some specifications, the British one would be a case in point, say simply, we won't bother them, the user of our specification, with figuring out the prying action. We'll simply say, if there's a possibility of prying action, and there would be here, then you have to increase the calculated force, P/4, by 30%. You just take it right off the top. And that's not a bad way of handling it. But in our case, in North American practice, you have to make that calculation. There are very, very few problems with bolts. There are disputes and arguments which are usually a matter of interpretation of specification requirements. And some of those issues I hope I'll address this afternoon. Real problems, it didn't function the way I thought it did, and bad things happened. What's bad things? Fell down, things like that. It's often where we have the bolts in tension, and particularly when there's fatigue. So fatigue, bolts in tension, prying action, that's a bad, an area where you have to exercise great care. The failure of the Kemper Arena, I was trying to think of the name. Where's the Kemper Arena? Is that in Kansas City? What, 15, 20 years ago? Big failure. That's a large roof truss consisting of large trusses going, let's say, north-south, and then supporting a roof system that goes east-west. The connection between those two systems was with the kind of, it's a lot busier than this, but the connection was basically the one that I've been illustrating in these last few images. And it's one of those situations where, and most failures are not unique to one feature. They're a combination of they didn't do this and they didn't do that, but one predominates. Certainly there was a lot of prying force in that connection, and that was a feature. Interesting that we don't want failures, but we should extract whatever information we can get from them and learn. Well, I was going through this list of bolts in shear, bolts in tension. Now, sometimes we have bolts in combined tension and shear. This would be an illustration. Think of the inclined force as a horizontal component and vertical component. We can always resolve any force into any components that we want. In this case, resolve it into horizontal and vertical components, and then it's a little easier to see that the bolts that fasten the T to the W-shaped column have to carry both a vertical component and a horizontal component, and that means shear and tension in the bolts. There's an interaction equation to cover that case. Got it? Got it. Next few minutes I want to spend on taking one bolt and following through the forces that are acting. I've done it kind of rather in a global way. Now I want to do it in a specific way. I've tried to encourage you in this idea of thinking of free body diagrams, and so let's carry on with that. So what free body diagram? Well, there's one. I cut more or less at the interface, and it's not in equilibrium at the moment. There's an applied force going to the left called P. It's not in equilibrium. The only place that a force can show up that will keep it in equilibrium is on that cut. And the only direction it can be is, in this case, to the right. So there it is. That's it. We call it whatever you want. We call it a shear force. That's the bolt in shear. And if you, for some reason, wanted it in stress terms, you would divide it by the cross-sectional area of the bolt and get a kind of an average figure. If you're doing LRFD, then you don't need stress, and if you're doing allowable stress design, then you need stress. Okay, so I have some information. Let's take the bolt out next and look at it. And at the moment, I know that there's a force on there, which we've called shear, has a value of P. And the figure I show is not in equilibrium yet. We know it has to be in equilibrium, otherwise things are flying apart. We can't have that. So how does this, how is equilibrium established here? Well, there's only physically one location where it can show up, and that's the plate is pulling against the bolt, and then I'll show the force here. It comes in like that. We call that, we like to label things, and we call that a bearing force. It's the plate bearing on the bolt. Okay? Okay, so we've got some more information. We'll come back and look at design rules for these issues. But let's take the next piece of information. There really is only one more. I'm going to do it pictorially. That force P, which I call the bearing force in the previous illustration, as you get into this view, the direction flips over. Free body diagrams will show that for you. And it's pushing into the plate. And now for equilibrium in the downhill sense, there must be forces in the cut section. This is a tension member. So that's the tension member design that we deal with. So we're going to have to deal with, we're not doing member design, we're doing connector design. So we'll deal with that bearing force and that shear force. So we identified the force in the bolt, shear force. We identified the force that the bolt imposed on the plate, that's a bearing force. And the force in the plate itself, in my illustration, it's a tension member, and that's a tension force. Not our problem this afternoon, but it's your problem as a designer. Now, everything I've illustrated is on the basis that there's no friction in this connection. It's what you would call a bearing type connection. There's no clamping force in the bolt. As I say at several locations through here, we're going to have to talk about that at length, but what I've been describing says there's no friction. It's just a bolt that's dropped in there. Maybe you didn't even put a nut on it. Now, design specifications. You've got so-called limit states design, or LRFD, or you've got allowable stress design. Historically, allowable stress design said find or identify the yield strength and apply factor of safety to it. Limit states design, which came along later, said use the maximum capacity of the element, in our case a bolt, or in your case something else, as the basis for design. And if we knew the relationship between those two, then of course the allowable stress design people and the LRFD people would be in harmony. But the world's not a perfect place, and for a long time, as it happened, the allowable stress design rules were behind, in our base of knowledge, the LRFD. You're at the point now, though, where that's been overcome, and that comes up in the next image or two. But I have said, and I want to reinforce the idea, that connection design always was done, whether you're an allowable stress person from the 70s, and there are some people who are here who were, or you never got taught that way and you just got taught using LRFD. The basis for the design rule, trust me, it was always the ultimate strength. And here's what happens for a bolt and shear. I'm going to show this in more detail in due course. Do you see a yield point? There is no yield point. Don't try to give me a rule based on yield. That's what allowable stress design did at that point in the way the specification presented it. But behind that was always the ultimate shear strength knocked down by a suitable factor. So this is one illustration. Others apply equally. It was always done on the basis of ultimate strength, which makes it awfully convenient for me to deal with LRFD and for you to deal with either one of the two. Now, your 2005 standard has these parallel lines for LRFD and allowable stress design. As you know, I expect, LRFD uses a resistance factor or knockdown factor called phi, and allowable stress design, just when you thought you were getting to know everything, introduces another Greek letter, which is capital what? Omega, sure. Oh, what a clever group. And you use loads that are appropriate for the system. In the LRFD system, it assumes that you're going to work, it demands that you're going to work with factored loads. You're going to say, there are the loads, I think, but they could be greater. Those are the factored loads. Somebody has to tell you what the load factors are. You can't do that reasonably on an individual basis. And in the other system, allowable stress design, we don't increase the loads. We handle it differently to come on another image.